Hi, I'm Leslie Kaelbling, and I'm very happy to be able to give this talk to everybody. I wish we were doing it in person. I want to talk about my general research goal, which is to make robots that are intelligent, flexible, and can solve any problem in any situation we might want them to do. So we want to make general purpose intelligent robots. And key to that, and different from many robotics projects at the moment, is a real desire to have generality and the ability to handle widely varying domains. For instance, imagine that you wanted to make a robot that could make tea in anybody's kitchen, or that could do any kind of household task. So there's a lot of talk right now going on about learning, planning, reasoning. What are the relative roles of these things? And I think it's important to disentangle that just a little bit before we start. So my view is that my problem is to be the robot factory. I want to think about how it is that I'm going to make robots that I can deliver out into the world that can solve the problems that they have to solve when they encounter the situations that they're going to be in. So I need to find some kind of mapping that goes in the robot's head, some mapping of its history of actions and observations into its next action. And the way I want to think about what that mapping should be is that I want to think about, in some sense, a distribution over possible situations the robot could find itself in. It could go to a variety of different houses. Those people could ask it to do a variety of different kinds of jobs. So there's some distribution over possible domains that this robot will have to behave well in. And my job is to find one good program that I can put, in some sense, in the head of all of my robots so that when they go out into the world they find themselves in, they can perform well. So what I think is good about taking this view is that, in some sense, given a distribution over the problems the robot might have to solve, there is this optimal strategy. But the bad news is that it's hard to find. So our engineering problem of finding the best program to put in the robot's head is really quite difficult. One thing that we can do is to think about the space of distributions of problems that the robot might face. So in one dimension, there's a kind of sense of the complexity of the variability of the set of problems the robot might have to address when it's out in the world. And in another dimension, we can think about how much we, sitting here in the factory, know about the world that the robot's going to find itself in. So classical engineering falls into this bottom left corner. There's some specific thing you want the robot to do, and you can just engineer that in advance. I would argue that the problems that are often solved in AI and planning have the character that we know the problem distribution very well in advance, but it's a very big set of problems. And so we might want the robot to do deliberation online. A lot of reinforcement learning, I would say, tries to address a set of questions where the behavior is relatively narrow. The particular thing the robot's supposed to do doesn't have very high variability, but where the engineer may not know in advance very well what it's supposed to do. But really, the set of problems I think that is most interesting are ones where we don't know exactly what the world is going to be like that the robot finds itself in, and the set of problems it's going to have to solve is very big and high variance. So how can we address that class of problems? So we can think about the general engineering strategy. How do we make a good policy for a given distribution? So our problem is that we have to pick a model class, and a way of finding a good strategy inside that model class. And we want to minimize the construction cost in the sense that we would like to make life easy for the human who has to specify the model and come up with simulator and maybe do learning. And we also have to make life easy for the machine, really both offline and online. So we want to pick some model classes where humans have insight, where we can do learning and optimization, and it all works well together. So I'm trying to really understand how to take everything we know about learning, everything we know about planning, and put it together in a way that will make robots that are generally able to solve a very big class of problems. So let's just take this motivating example now. So I'm going to spend some time talking about the problem setting. So imagine that you have a robot that has to solve the problem of doing something in this kitchen. You might look at the kitchen and wonder where the fork is. But what makes this problem hard? What makes the problem of, let's say, making dinner in this kitchen seem very difficult. So one thing is that the state space is very big. Robotics people like to talk about the number of degrees of freedom their robot has, but here, imagine the number of degrees of freedom that the kitchen has. How many state variables are there? Right? We can't even enumerate them. The horizon is really long. The number of steps you'd have to take to make good progress in solving a problem in this kitchen seems very, very long. And there's deep and unavoidable uncertainty. In robotics, often people say that rather than focusing on reasoning under uncertainty, we should focus on making better sensors. But here, there's fundamental uncertainty that sensors won't solve. They won't tell us what's in this mysterious blue container or when the people are coming home. So we have to really address all of these problems head on. I have a ton of things that I would like to talk to this community about and not enough time. And so I'm gonna just kind of blast through a whole bunch of issues and ideas and things that we've been doing that I hope are of interest to you, and that maybe I can inspire you to help me work on some problems I care about. So first I'm gonna talk about planning, and I'm gonna talk about the spaces that we have to do planning in and the strategies that we use for doing that planning. So first of all, let's talk about robot manipulation planning. So imagine that there's no uncertainty, but we're thinking about how the robot can interact with the objects in its world. So you might imagine trying to plan in some kind of raw space, in a simulator space or the space of the actual robot, taking small actions. But the horizon is really long, and it's very difficult to imagine what kind of a heuristic we would use to plan in that situation. And so what we do is think about abstract models that let us do planning more efficiently. And so we're going to currently propose a model that mixes discrete and continuous planning in a way that I hope you'll find interesting. So first of all, we have to think about, if we're going to make an abstraction, what makes it useful, right? So it should make the computational problem easier. That's why we're doing it. Generally, it might make our solution quality worse, but we hope it doesn't make too much worse and that it applies to lots of problems we care about. So it's just interesting to look at this figure for a minute. This is a set of problems that was proposed as a benchmark for meta-learning. And what's interesting is that problems are a combination of relatively simple robot manipulations, things like pushing objects and picking them up and putting them down, in some cases with very little variability between the tasks. And so the question is, can we just think about the robot manipulation problem in a way that would solve all of these problems? So most of you are familiar with problems of motion planning, right? So we're given a start and goal position of the robot and some configuration space, so we'd like to find a collision-free path. There are exact algorithms for solving these problems that are difficult to implement, although provably efficient in a certain sense in practice. Mostly people use things like RRT, which are methods that sample configurations in the world, try to connect them, and use an understanding of the space that they're operating in to be sure that they bias the sampling in a way that will be moved toward a goal potentially and also cover the space. So can we take these ideas and apply them to more general manipulation planning? That's a question. So to do that, we really need to understand the space that we have to plan in when we're thinking about manipulation. And so there's a very nice model of this manipulation planning called multimodal motion planning. And so I want to talk about that a little bit. So let's imagine for right now that we're solving a problem where we have a jointed robot and it has to pick up objects and move them around and put them down. And those objects are rigid. So we can talk about the notion of a mode. Mode is, you can think of it as a smooth subpart of the space that we're operating in, where the robot is moving smoothly and changing only a small set of state variables. Because if I'm in a world where there are lots of objects, then the state variables in the world include not only the robot's configurations, but also the positions and orientations of the other objects. So if the robot is moving in free space, then as it changes its joints, it changes only some variables in the world. But if I'm holding an object, if the robot's holding an object and I move now, then I'm not only changing the state variables of the robot, I'm changing the position and orientation of the pencil. So a mode is a smooth set of dynamics, but we can have different modes that we move through. So a mode family is a set of modes with the same changing variables, but different values of static variables. I'm going to introduce this now in a picture, which will be easier to grasp. So this is a great picture that comes from a paper. This is an older idea, but this is a very nice illustration. So consider the green manifold in the upper left-hand corner there. You can imagine that that's a subspace that just corresponds to the robot moving itself, not changing any other objects. So there's a very high dimensional state space, which is the positions and orientations of all the objects. And there's, in this case, a low dimensional manifold, which is the space that the robot can move along when it's not holding anything. And it doesn't change any other state variables, it only changes its own variables. But now imagine that we wanted to pick up and move the pencil. Well, we would come over here, we would move through the green manifold until we were at a point where we could grab the pencil. And now if we attach ourselves to the pencil and move the robot, we're moving now in the purple submanifold, which is where we're actually changing some of the pencil's variables too. We can put the pencil down and move ourselves again. And now we're moving in a green manifold, but it's a little bit of a different one because it's one where the pencil is in a different place than it was in before. So the topology of the space is very interesting, and it helps us think about planning. It helps us imagine mode switches, which is where we change discretely what mode we're in, and then moving through modes, which is where we move continuously on a submanifold. And this helps us actually, it corresponds to a kind of operator description level characterization of the dynamics of the world. So we could describe, for instance, picking up an object, which is actually a change of mode, using operator description language that will be very familiar to everyone. Like we might say, the result of this picking operation is that we're in a new mode. And the mode that we're in is one where we're holding the object with a particular hand in a grasp. And it might have some preconditions, like we're not holding anything and the object is in a certain place and the robot is somewhere and there's free space that we can move through and without collisions. And there might be constraints on some of these continuous values. Like we might have to say that, well, this particular grasp of the object is valid in some way, or that the robot's kinematics are such that when it's in a particular configuration, in fact, we can grasp the object and so on. So what we do is we actually write down operator descriptions that characterize discrete conditions that describe the mode or the mode family, and also continuous variables that vary within a mode. So we wrote down some mode descriptions. We described mode families for moving through free space, for picking up an object and moving while holding it, and then putting the object down, for pushing objects, for operating things like a valve. But we really only had to write about 11 operator descriptions, very generic operator descriptions in order to describe the whole domain. And that allowed us to make plans to solve that whole set of tasks, which were kind of viewed in the reinforcement learning world as tasks that should be learned separately, although the task set was designed because there was a hope that one could learn to solve one task and then somehow use what was learned to solve one task to solve the other ones. But we were just able to write them down as planning problems and solve them as planning problems, given the files that described how the world worked. Some of them were trickier and need some extra mode descriptions in order to solve them. But I just want to illustrate the range of interesting planning problems that come up for robots in interaction with the world. Okay, so that was meant to illustrate planning where we have to deal with motion through continuous spaces and also discrete changes in the dynamics of the world. But of course, in any real robot, there's uncertainty and maybe substantial uncertainty. And everybody knows by now that like trying to optimally solve problems under uncertainty is really hopelessly complicated. And so we're gonna take some shortcuts that still give us pretty robust and interesting and reliable behavior. So I'm gonna tell you about that now. First, I wanna give you though, a hint of the kind of a belief space that our robot operates in. So our real robot, when it's interacting with the world, it has uncertainty about all kinds of things. It represents uncertainty about the occupancy of space. It represents a set of object hypotheses, objects it thinks might exist in the world, including distributions over their type and continuous parameters and their relative poses and so on. And so it's a very complicated belief state that the robot has, a belief distributional estimate of what's going on in the world around it. The approach that we take to actually planning and execution is a replanning approach. So what we do is we say, we're going to do state estimation, and based on our belief, we'll make a plan. We'll execute the first step, see what happens, re-estimate, and make a new plan. And that gives us the license to be very approximate in our planning, because we assume that we'll be able to observe the results of the action that we took and replan if we need to. Now, of course, this isn't optimal, but it does let us address relatively big and difficult problems. I want to illustrate the idea of replanning in belief space, though, and I'm going to do it first in a very simple domain and then work my way up to our real robot domain. So let's take a really, really simple example. Imagine that we have a point robot in XY space. So this is like the easiest kind of robot in the whole world. And that it's trying to arrive at some location and to believe it's there with high probability. But it's not very well able in the left half of its domain, in this dark part of the domain, to sense where it is. But over in the lighter part of the domain, it can sense where it is well. So imagine that its initial belief is very big, like it's pretty confused about where it is, and it wants to arrive at this goal belief with very small variance. How can we think about planning for that robot? Well, one way to think about it is that it's an underactuated robot. It's a kind of robot that has trouble controlling some aspects of its state. So you could think of it as having its state being a belief state now. So its belief might be a mean and a covariance. The planning objective is to be at some location, maybe not with zero variance, but with low variance. And we could think of this as a kind of a planning problem that robotics people think about, like trying to control this robot with only a controller at one of the joints. But what's difficult to think about is what are the dynamics of the process in belief space? So how can we formulate this problem? So generally speaking, what we have to do is we have to think about the dynamics, which give us, we should be able to take a previous belief state and an action and get a new belief state. But we can't quite do that. So what we can do is use some kind of Kalman filter. What a Kalman filter would do is it says, well, given my previous belief, excuse me, mu t and sigma t, given my previous belief and an action and an observation, I can compute a new belief. So that gives us the actual underlying dynamics of the belief process. But the problem is that we can't use it very well for planning, or certainly not for deterministic planning, because we don't know what observations we're going to get. So what we do is we substitute in for the observation some notion of the mean or most likely observation that we might get given our current belief. If we do that, now we have a deterministic belief model. It's approximate, but it's a dynamics. And then we can use tricks from control theory and continuous optimization and so on to plan a trajectory. So we want to find a trajectory that has low variance and the final state and is relatively low cost. But note that this is a trajectory through belief space. So now, given this trajectory through belief space, so this is an example, maybe we start out with high variance here, and our trajectory that we get by planning says, well, what we're going to do is we're going to kind of drive the mean along this dark arrow, and our variance is going to decrease, and then we're going to run over here to the goal belief. And in this very simple problem, we have no uncertainty. There's no uncertainty in transitions. So once we get localized well over here, we're good to go. Okay, but this trajectory was made under the assumption that we were always going to get an observation that confirmed, in some sense, our belief about where we were. But of course, that's not necessarily going to happen. So when we get observations, they might drive us off that trajectory. And if they do, then we need to replan. So what's interesting is that we get behavior that's like the following. So let me just walk you through this figure. So imagine that we start out with this big uncertainty about where we are. And imagine that, in fact, we're really over here. So this plus actually indicates where the robot really was. So as the robot goes, it begins to drive itself along this trajectory. But as it drives in this direction, it gets more observations, and eventually it realizes that actually it's down lower than it expected. So it replans a new trajectory, and then it gets more observations and it replans a new trajectory. And what we find is that the actual trajectory of the robot is that it starts to go down, but as it goes down, it's going over here and it's getting better and better at observations. And now it's realizing, actually, I'm down here, I'm now below where I wanted to be, and it comes back and it runs back to where it needs to be. So this idea of determinizing planning and belief space has two important properties. One is that it still forces us to gain observations, but the other one is that we can use kind of classical planning, deterministic planning strategies. In geometry now, this becomes more complicated because we have uncertainty about the positions of objects or the position of the robot. And we have to think about how we can do geometric style planning and problems where we have uncertainty. And we do it using this notion of a shadow of an object. So imagine that the robot has some covariance of representing its uncertainty about its position with respect to this table. Well, we can build a kind of geometric confidence interval, you can think of it as, on the space that that table is taking up relative to the robot and use that in our planning. That lets us do planning in belief space with geometry, where the robot plans to both move and to look at objects to reduce its uncertainty relative to the objects. So we might end up in a situation like this, where we start out with these two objects and their shadows. The robot starts here and it would like to be there. And it can plan to move as it moves. The uncertainty about its relative position to the objects grows because there's uncertainty in the robot's actions. Then it could plan to, then it could look, reduce the uncertainty, move, look, and move again. So we take this strategy when we're planning for our robot, and we can make these kinds of shadows for very complicated objects. So the image on the left shows a shadow with a lot of uncertainty of the robot relative to the table, and the one on right with less uncertainty. Okay, so how do we do planning? How do we represent problems for planning when we have both uncertainty and geometry? So first, let me talk about the uncertainty part and then talk about the geometry part. So how do we represent uncertainty using kind of classical planning style representations? So again, we'll look at a very simple model. Here's one where there's only 3 discrete states in the world. So a belief is represented by, you could think of it as a point in the simplex. There's the probability that it's in each of the states. So we can write fluents down. We can use the language of logic to talk about sets of belief states. So for instance, I could say, I believe, so the phi is a state variable and v is a value. I can write fluents in a form that looks like this, which basically mean that I believe that this variable has this value with probability greater than or equal to p. So in the simple case where I have a discrete 3-valued variable, that belief state corresponds to this like upper corner of the simplex. Another useful kind of belief fluent is to say roughly, I know the value of phi. So I might say, or it's not quite I know, I believe with high probability the value of p. So what's interesting here is that it actually corresponds to all 3 corners of the simplex, right? So I know the value of p is something that says, it doesn't specify which value, it just says there is a value such that I know the value. And that kind of formulation is useful for talking about the effects of actions, because I might say, after I look in the box, I'll know what's in there. And I can write that down as an operation, as an operator description in belief space. Using these ideas, we could formulate a simple problem. I'm not going to go through this in detail, but just to give you an idea, here's a robot that might be looking for an object in some discrete space. And we can write down operators that look a little bit like PDDL operators, but they have some continuous parameters. Now the continuous parameters correspond to probabilities. But we can talk about how, for instance, if the robot wants to move an object from some place to some other place, then it needs to believe with some probability that the object is in the starting place, and there's going to be some resulting belief that the object is in the termination place. We can also write down operators that describe the ways in which the robot will become more certain with high probability by looking in locations and gathering information. So we can make plans using this kind of a representation. And when I talk to non-ICAPS people, I have to emphasize how cool it is that these operators are lifted and abstracted away from the particular objects and locations, but I don't have to tell you about that. If I have continuous quantities and beliefs, I can still write down fluents, kind of logical looking specifications for sets of belief states. So one example is that I might say that imagine that now I want to talk about the pose of an object, let's say relative to the robot. I might specify the pose of the object, the mean pose, some variance, maybe it's a diagonal variance on the pose, a condition on the mean, and a likelihood that the object is actually governed by this component of something like a mixture distribution. So there are ways of talking about whole sets of continuous distributions using logic-looking language. Okay, so I have now ways of talking about reasoning about geometry and about belief, combining discrete and continuous aspects and so on. And now the question is, what kind of planning methods can we use in these types of problems? And in our group, we've explored a couple of different strategies, and other people have strategies too. I'm just going to outline them very briefly. So one important thing, though, is that pure forward search, so just looking at little steps in belief spaces, or even in mixed continuous and discrete space, is probably not going to work. And we need to consider planning methods that actually carefully understand the relationship between discrete changes and continuous changes in the world. And it's really important to understand that there's a close, tight interleaving between discrete choices, like which objects to move and in which order, and continuous choices, like how to grasp something. So in this example, the robot had to move something out of the way, and it has to re-grasp this object. So the way it originally picked it up, it couldn't actually put it back in this narrow place that it had to put it into. So the geometry tells you things about what you have to do, which discrete choices you have to make. So you can't just make a pure abstraction into two levels. So one strategy that we use in the belief space planning is a kind of goal regression. So this is an old idea which has been repudiated by most of planning, I understand, but it turns out to be useful for us because our belief states are very complicated, right? They're the whole occupancy grid and a complicated representation of what the robot knows in the world. And there's just no convenient way to, or accurate enough way to take that complicated belief and write it down in a set of fluents that I could just pour into a PDDL planner. So instead we use fluents that involve continuous and discrete values and also probabilities. And we do regression style reasoning. So we write down a description of the goal using these fluents, and then we compute in some sense sub-goals using that same language, and we do regression until we hit a sub-goal that our current belief satisfies. So as long as we have a test, as long as we can ask the question, does our current belief state satisfy this description, then we can do this kind of backward chaining without ever having to represent the belief state in a language that the planner can actually operate on. So that turns out, at least for us, to be an important idea. Another strategy, which we've especially used in the case of continuous and discrete planning, and a little bit also in belief space, is this planner developed by a student named Kaelbling called PDDLStream. And the way it works is that it actually adopts PDDL as its internal kind of inner loop. And what it tries to do is construct a domain, actually a discrete domain, that represents the true problem well enough so that if it finds a solution in the discrete representation, that will be a representation to the overall problem. The important point, though, is that we can't just do this abstraction once, right? We might love the idea that we could take our problem, somehow map it into a sub-problem that is describable in PDDL and get a plan out and be done. So that would be awesome, but it generally doesn't work. Because there are many continuous quantities in our worlds. There are things like object poses of objects on the tables, positions of the robot, even probabilities, belief states, paths, all these things are continuous. And we don't know in advance, and we cannot know in advance, which particular values of these quantities are going to be important to us in planning. This is a really important point. we can't afford to pre-discretize our spaces finely enough that we could just pour all those samples into our planner at once and plan with a discrete domain. Instead, what we have to do is a kind of an iterative process where we try to make a plan with the current sort of set of samples we have that describe how the world works. If we make a plan, it's great and we have a solution to our problem. But if we don't make a plan, we can get guidance from the ways in which the planner failed in order to sample new values of the continuous parameters. So that's a really important idea. It might be that when I first decide to clean my room, I only reason about moving a few objects. And so I would only need to start by sampling poses for those objects. But during the course of planning, I might realize that I have to think about opening a drawer or putting something in the other room because stuff doesn't fit here. And now I would want to get samples of positions and configurations of those objects that I hadn't been thinking about before. So I can't possibly sample the whole space in advance. And sampling is tricky, right? So it's not in plain old robot motion planning, generating samples that you could consider the robot reaching is usually not too hard. But once we start to think about these multimodal spaces with these low dimensional manifolds, then finding, for instance, a sample of a pose where the object is sitting on the stove is not easy. And if we generate samples at random, most of them won't be good. Similarly, for kinematics, if we want to find a sample of where the robot could pick up the object off the stove, well, we can try to find some, but it's random sampling won't really help very much. So we have to think about managing the sampling process. We have to think about ways of biasing it potentially, and also managing it in the loop of doing planning. So the idea that really lets us do that is this idea of a stream. So when you specify a problem to PDDLStream, you write down operator descriptions, which will look very familiar to you, but you also specify streams, and streams are little encapsulated generators that can give out typed values that satisfy certain constraints. So for instance, here's a stream, it's what we call a conditional stream. You give it the pose of an object and the robot's grasp as input, and it gives you out samples of configurations that the robot could have such that they satisfy constraints, they satisfy kinematic constraints. So one way to think about it is that we're generating values of possible new constants in the world that can come with a certificate that they satisfy new static predicates that we didn't know about before. So they can produce a potentially infinite sequence of typed output values. They can be conditioned on discrete values or continuous values, and the values they output are guaranteed to stand in certain relationships to the values that came in. So they generate new static facts. Okay, so PDDLStream is a way of solving problems, and we're enthusiastic about that. And if you wanted to try it, you could do that. Another idea that we have just been playing with recently, but other people have used to good effect, is the idea of searching in the space of skeletons. Well, so we're getting close to Halloween, so I figured I'd put a skeleton on the slide. So a skeleton, you can think of a skeleton of a plan as a sequence of operator templates, really. And maybe even with the discrete parameters filled in. Like I'm going to pick up object A and then I'm going to put it down, and then I'm going to pick up object C and I'm going to open the drawer. So you could come up with a plan that's just these operators with the discrete parameters selected. And the inner search would be to say, given a skeleton, can we find values of the continuous parameters, including motion paths and potentially probabilities, that satisfy? So that's also an interesting structure for planning that might be something that you could think about pursuing. One person who's been very successful with this method is Marc Toussaint. So he has this idea of logic geometric programming, and his strategy does discrete search on the outside using branch and bound, and a kind of continuous optimization method on the inside. And he's gotten robots to solve really interesting problems this way. Okay, quickly, something about execution. So we want to solve really long horizon problems, and it's much too long to plan. So what we do instead is we use hierarchy, but we use hierarchy in a more aggressive way than is typically done, which is to say that we make a plan at a hierarchical level of abstraction using the old abstract technique of postponing some preconditions in order to make an abstract model. But then rather than trying to refine the whole plan, we pick the first sub-goal in the abstract plan and just plan for that at more detail, and pick the first sub-goal of that and plan for that in more detail, and so on, until we have a primitive, let's say this P1 here, that we can execute. So now we execute that primitive action in the world, get an observation, do a belief update, and now we ask ourselves, what should we do next? And one thing about this hierarchical stack of plans, right, you can think of this as a stack of plans, is that it gives us a good way to do replanning and reconsideration. So rather than replanning again from the top, given our new belief state, we can ask ourselves whether we are still, in some sense, in the pre-image of the plans that we have. We ask ourselves, are we, so in executing this primitive action, we expected to arrive in a state that satisfied this sub-goal. And if we do, that's awesome. And what we would do next is we would plan for the next sub-goal, because this isn't a primitive action. But if we didn't land here, we would ask ourselves, well, did we land in the pre-images of any of the steps of this plan? And if we did, if we happened to like just pop ahead to here because we're lucky, we would execute this action next. If we happened to just do a no-op, nothing happened, then we would re-execute this action. If this whole plan is now irrelevant, we would pop it off the stack and go up here and replan only at this level of abstraction. So this kind of hierarchical planning and execution lets us do replanning efficiently because we only have to reevaluate locally. And it also keeps us from having to make detailed plans for a future that we will not be able to predict very well. So in many of our problems, this part of the plan might involve gathering information that will allow us to execute these things later on. It does come up with a price, right? The price is that we risk arriving in a situation where we won't be able to plan. And so we hope that the domains we operate in don't have irretrievably bad outcomes, or if they do have very bad outcomes, that by using learning, which I'll talk about in a little bit, we can bias our choices of how to do these things in a way that doesn't get us into too much trouble. Okay, as a result of this, we can make a robot that does a bunch of things. I'm going to show you the video, but I'm going to give you a caveat, which is that any individual thing this robot does, somebody else could make a robot do more beautifully or more efficiently. But what's important is that this is doing general purpose state estimation, general planning, reasoning, reconsideration, so on. And the same code is going to do all these things. So here we asked the robot to put the blue box where the can is, and it saw the can was in the way, moved it out of the way, got the blue box, figured out where to put it. Here we asked it to put the green box in the corner of the table. It realized that the orange box was in the way because it has to push the green box because the green box is too big to pick up. It also knows that its pushing is really unreliable. And so it plans to look, it's planning in belief space, it plans to look to be sure the object got where it wanted to. Here we asked it to go out of the lab. It saw these chairs were in the way. It's planned to move the chairs. It moved the first chair out of the way. The second chair, it just brought with it because we told it should get out of the lab, but we didn't tell it what to do with the chair. Here we asked it to put a full oil bottle on the other table, and it's actually doing belief-based planning and picking up the oil bottles to see what's full and what's not. Okay, and all these examples, though, these are mostly implemented by me and my colleague, Tommaso Zona-Perez. And in all those examples, the only learning that was done by us and not by the robot. So now let's think a little bit about how learning can improve what's going on here, right? Because although that was kind of cool, we think, it was also a lot of work to code the operator descriptions and the details of the models for estimation and so on. So one thing I think that's important to think about is that there's really two different kinds of learning that we could do in a system like this. So some of the learning is really learning about the world, understanding how to detect objects or to do primitive control and learning transition and observation models. And there's also a whole set of other kinds of learning that are really learning to reason. So I'm going to show you now some examples of learning models and learning to reason. So let's think about learning models. In particular, let's imagine that we wanted to take that robot that I just showed you and integrate a new skill into its repertoire. Well, so we don't want to have to relearn everything that this robot already knows. So assume that maybe we've used reinforcement learning to learn a basic controller for something like cutting or pouring. And now we would like to figure out how to take that basic skill and add it into the repertoire of the robot. So let's take the example of pouring. So imagine that we have this situation where we can pour from one object into another, and we would like to describe it in some operator description so that we can throw this pouring ability into our general set of things the robot can do. Then we would write an operator description like this. We might have preconditions that say the source container has liquid in it, and we're holding the source using some continuous grasp parameter. The source container has some shape. The destination container has some shape. There's a relative positioning between the two things. And what we're interested in learning, because it's hard to anticipate, is a constraint that relates all of these continuous quantities, the shapes of the objects, their relative positions, maybe the gain parameter that we use in the pouring and so on. So there's some constraint on all these continuous parameters such that if that constraint is satisfied, the pouring will be successful. And the question is, what is that constraint? So we do learning by generating pouring in many different kinds of circumstances, and using a Gaussian process regression method, we learn to score certain kinds of, we learn to score possible pouring instances. And that helps us understand under what circumstances a pouring operation will be successful and when it won't. We use a GP because it gives us an understanding of where we're certain and uncertain about the space. So it also helps us drive exploration. So we can sample in places where we're uncertain, hoping to be more sure about where the pouring will be effective. Another reason for learning a Gaussian process, which is learning a scoring function, learning to map possible pouring arrangements into how good they are, is that lets us do sampling later on. So instead of learning only one strategy for pouring, which might be a super awesome, perfect way of pouring, we try to learn the whole locus of good pouring maneuvers. So for instance, if we were blocked for some reason from pouring this way, we could pour backhanded instead. So that's an important aspect of the learning. When we're going to integrate it into planning, we need to have this variability. Training on the real robot is expensive. I just wanted to show you this. We had to pick up a lot of chickpeas. So you want to do as few experiments as possible. But we also used planning actually during the course of gathering training data. So having learned operator descriptions, in this case for pushing and for pouring, we were able to integrate them into the planner. In this case, it's using the PDDLstream planner. And we can put the objects on the table however we want to, and the robot can perceive them. And we give it goals that involve what objects should be where in the table and what stuff should be where whether the stuff that we can pour should be in the bowl or in the white bowl or where. And the robot can do these things. And it synthesizes new plans every time. So we didn't can anything in advance. And it does actions that it needs to. So in the first case, it moved an object out of the way. This is a nice example. It pushed the red bowl in front of it because with the red bowl in its original position, it wasn't able to reach over there. So that's an example of the geometry actually dictating the discrete action sequence. So there it did this again. So it pushed the bowl over and then came back here and poured the stuff in. And we'll look at one more example and then go on to something else. Here's one where it had to put the object on top of the other one and pour into it and so on. So it's a general purpose planning and execution. Another thing that we've been focused on is learning search control. So this is learning to reason. AlphaZero works very well by learning how to control its planning. we're interested in very aggressive generalizations. So in this particular piece of work, we had the robot learn from moving big objects, as it does over here on the right, to be able to be more efficient to make plans for moving small objects like the ones in the cupboard. We do this by learning a queue function at an abstract level that helps it decide among the discrete actions. And we learn this abstract queue function by a combination of graph neural networks and some hand-designed logical predicates that pick out the structure of the graph in the graph neural network. So doing this, I'm not going to have time for the details here, but again, training only on moving a single large object. If we use an existing algorithm for planning, it works pretty well. If we use a simple heuristic, it works great in 2 cases, and it can't move the big objects, all the big objects at all. But if we do this learning of the abstract queue function, then we can learn more efficiently. And just to emphasize, right, we trained it on only trying to move this one red object. But to move this one red object into the other room, it has to move several green ones out of the way. But just from that, it was able to generalize to moving all the green objects into the apartment and to generalize to moving objects within the cupboard. One last example of learning is learning to map a complicated domain into a smaller one. And the idea is that we're going to adopt constraints to make the planning problem easier. So here's a robot that has to get itself over into where the red object is and move the red object. And by constraining itself, adopting a constraint of not going into some of the rooms, it can reduce the size of its planning problem. So now it plans in a subproblem, and it's able to make a plan and execute it efficiently. So it runs over there, it has to move some objects out of the way still, but it's able to do that. And similarly here, it has the problem of putting those red objects over in the cubby holes in the bottom. And it is able to learn to predict that it can ignore some objects and some state variables. And that lets it reduce the dimensionality of the problem. It makes a plan in the low dimensional problem, and then it's able to execute it in the high dimensional problem. So all of this that I've talked about is work of my colleague Tomas and many of our students. And just for fun, you can watch the robot, just so that you know it was real, you can watch the robot make some mistakes. And I just want to, I'm happy to talk to ICAPS people. I look forward to answering your questions when we get to do question answering. And I hope that we can find a way to make some of the problems that I've shown you accessible for more people to work on and think about, because we could certainly use your help. Thanks very much.